What happened there? Okay. Well, welcome everyone. Glad you could make it. Like Jeff said, we're very pleased to have such a large group this year. Unfortunately, we couldn't take more, but please do bear with us as things might be a little tight. And we look to have a really good week. Hopefully you'll get a great overview, some practical experience, and be able to take some of this back to your own research groups and start to implement some high throughput phenotyping approaches, different methodology, and take some of these concepts and put them into practice to accelerate our breeding and genetics and all of the crop improvement that we're working on. So I have the pleasure to give just a general overview of things that we'll look at this week, and to welcome you and to give an overview of the project and where things are at. So really the scope of largely what we focus is thinking about plant breeding and genetics and thinking about present and future constraints. And so if we look at genomics and the revolution in high throughput sequencing over the past 5 to 10 years, this has given us a wealth of genomic information, and at that same time there's been limited advances in the way we collect plant phenotypes. And so now we can look at this paradigm where our genomic information vastly outweighs phenotypic information. And so whether you're working in genetics, whether you're running an applied breeding program, every bit of phenotypic information that you have becomes more and more valuable because it's expensive, it's time-consuming, and difficult to collect. And so through this project, through this workshop, what we're looking at are some of the needs and challenges in phenotyping. And hopefully you can start to see some solutions, some promising avenues for addressing this constraint and making phenotypic data and phenotypic information more abundant, easier to collect, and balance out this scale, which will, in the end, help to accelerate all of our research programs. And so in the scope of genomics, we often think about taking the genotype and connecting it to a phenotype. And this is kind of this black box that we call biology. And so in the functional biology world, trying to understand how we take DNA and it's translated, transcribed, and into protein networks and something that gives us a phenotype. And so largely in quantitative genetics, what we're taking is lots of phenotypic observations and correlate those back to a genotype to look for some causal variant. At the same time, in breeding, we want to take those genotypic information and predict forward what that genotype would be to make advanced selections ahead of the time spent on phenotyping. And so overall, this paradigm goes back and forth, connecting genotype to phenotype, and having balanced and good information on both sides of the equation is really critical. And so you'll hear a lot about this week, but high throughput phenotyping is really this multidisciplinary approach. And so it's this intersection of plant breeding and genetics, physiology, bioinformatics, engineering. And so you'll see a lot on the engineering platforms, how we need good engineers and engineering solutions to be able to deploy these platforms and equipment in the field. Breeding and genetics to really define the direction and the phenotypes that are needed, the type of populations that we should be working with. And the physiology, so we can use a lot of different types of sensors, but to put these in a physiological context to where we're taking relevant measurements in the right context at the right time. And then bioinformatics, and so you'll get a scope this week on some of the informatics tools that we can use to analyze high throughput data. But in the end, it becomes, again, a big data challenge. And so having members on your team that span these different disciplines is really what's needed for successful implementation of high throughput phenotyping. So keep that in mind over the scope of the week as you look at your institution, at your research programs, being able to put a good collaborative team together that span these different disciplines is something that we've found is really critical to having any type of success in high throughput phenotyping. And so you'll hear a lot this week about how this is really a scope of precision ag meeting plant genetics. And so these are two of the guys in my group and our small plot drill. But you'll notice here on the top is a GPS unit, and you can't see the hardware, but this little tractor is on auto guidance, and the drill uses the GPS to trip on each one of the ranges. And so this is just one of the pieces in that total program that we found becomes really critical for implementing, especially geospatial high throughput phenotyping approaches, to be able to lay field plots out on a precision grid, and then that follows on being able to use automated high throughput phenotyping approach on those. And so with that, you're able to put very precise planting of ranges and columns with this type of equipment. So in the scope of building a program that focuses on utilizing high throughput phenotyping, there's a lot of caveats, a lot of pieces to put together, and so this gets back to having a good team in place to cover all of those different disciplines. And so some of the things we'll cover this week, we'll just briefly touch on some different platforms. We're mostly going to focus on this concept of what we call georeference proximal sensing. And so the integration of different types of sensors, a high precision GPS to reference all of those data points, and then the approaches that you can use to assign that data back to individual plots to extract plot level values. And so this just a brief overview. You'll hear this iterated over several times in different ways. But like we said, to physiologically define the proximal measurements, so what type of sensors, what timing and what type of measurements to be taking, using a precision GPS to mark each one of those data points and be able to place those back within a field plot within the experiment, and then different types of sensors or imaging arrays to be able to collect those data proximally with the scope of non-contact high throughput phenotyping. And so just some ideas on configuration, and I'm just gonna briefly touch on this, and there'll be others who will really go into these on details. But like we said, having different arrays of sensors that are working in parallel here, taking a very high sampling rate, and so many sampling per second, at the same time having GPS to locate and orient across those field plots. And so what this looks like then when the data starts coming back is that we can reference each one of these data points on a latitude and longitude coordinate system. And so Kelly and others will describe this system in detail, talk about how we can use the georeferencing approach to look at field plots. And so just for example, on this system, we have a GPS on the left and right side. These are sampling at 10 times per second at 10 hertz. And you can see for each one of these GPS sampling locations, you can see approximated within there is the sampling position of each one of the sensors. And so you can see turning around at the end of the field, this is bare soil, and these are NDVI values. So a normalized difference vegetation index, you'll learn much more about that as well, and basically a measure of greenness in those plots. And so you can see low values here for the bare soil, and then the higher values as you move into the field experiment. And so being able to reference these on a geocoordinate system, being able to triangulate the position of each one of those individual sensors, and then being able to extrapolate field plot information and individual sensor measurements within those field plots. And so these are all things that we'll go through this week to get a good foundational grasp on this approach, on this concept. And so what this looks like, kind of as I quickly go through this on a bird's eye view, is to look at an entire field that we phenotyped here 2 years back, And you can see here again low values on the end of the field where we turn around. You can see field level variation. And so here is a poor area of the field where generally the NDVI values are low. You can see a gradient kind of across the field this way. And there's overall 1,000 different plots in this field. And so you can also see on these adjacent field plots, plot-to-plot variation, which in the scope of breeding and genetics is what we are primarily interested in measuring, are the genetic differences between different entries in the experiment. And so we'll go into this in depth, but just the concept of if you zoom in on a small area of that, and these sensors are continually taking measurements along the field, using different coordinate system to be able to identify and define the plot coordinate boundaries of the field plots, and then basically trimming out the data that would be in the alleyways between plots. Based on the row column design of that experiment, we can then assign that data back to individual plots. And so you can see here on this particular field experiment, actually very contrasting differences between adjacent plots for this NDVI measurements. And so this is really the georeferencing approach that we'll go through this week, learning how to take all the way from the sensor data, what this data should look like, what this data looks like coming in, how that's georeferenced and processed, and then how we can use the geospatial field design to assign that data then to individual experiments within the field. So the other thing that we'll look at this week thinking about is when we're able to do this high throughput phenotyping, what kind of research does that open up to us? And so this is just an example of that same field measured over 3 different time points. And so when you're able to take field measurements on the order of an hour or a few hours rather than days, this enables temporal sampling across the growing season. So we can start to look at dynamic differences in those plots across the season. And so you can see dynamic difference both across the temporal range here, but also within these different plots, you can see very variable differential response during that growing season as these breeding lines start to senesce. And so this gives us this rapid assessment with repeated measurements over the time. And so what it's showing here is just a sample of those plots out of that experiment from the first measurement date actually through 4 measurement dates. And this again is NDVI, so a measure of plant health, a measure of greenness on those plots. And so this would be from right at heading in winter wheat through physiological maturity. And so you can see that most of the lines start out about the same and they end pretty much at full senescence. However, there's a very differential response between the genotypes during that time period. And so if we're only measuring at, say, a single time point, whether it be here or here, you really miss those dynamic response over time. And so we're going to look at then, again, also how to use high-throughput phenotyping in a time series approach to be able to capture these dynamic differences and then start to model them and use them to understand the genetics to make better selections in the breeding programs. Just to touch on, we'll briefly talk this week about UAV and thinking about different platforms that can be available for phenotyping. Our primary focus for the week will be on this ground-based high-clearance tractor vehicle, but to look at some of the potential for UAV and other platforms, and then how we can integrate these as well into the same type of high-throughput phenotyping approach. And then we'll touch on some future developments, things that are coming online now and have great potential in the future, thinking about novel types of sensors, how they can be integrated into this same georeferencing approach, and talk about the future for automated processing algorithms, machine learning and deep learning approaches. And then we can really start to dream about the day when we can get a hold of some military-grade technology and have ground-penetrating radar from our UAV. And so to bring this back, really in the scope of high-throughput phenotyping, we're talking about this genotype to phenotype paradigm. But we're primarily interested in some phenotype like yield, water use efficiency, leaf area index, things that we're not going to measure directly. And so keep in mind that in the scope of high-throughput phenotyping, what we're talking about are phenotypes that are amenable to proximal and remote sensing, that we can use one phenotype to basically build a model or use that secondary phenotype to predict our primary phenotype of interest, whether that's through a direct correlation or an inverse modeling approach. We're using a proximal set of phenotypes to predict more difficult phenotypes of interest. And so keep in mind that this is the scope that we'll be thinking about in high-throughput phenotyping. And so just to give kind of the workshop overview in the scope of this high-throughput phenotyping process, you really have these entities of data collection, data processing, and then genetic analysis. And some key pieces in here are obviously in the data collection. We'll have time at the beginning, a few days here, to look at platforms and sensors, to look at different options and how these can be integrated into a high-throughput phenotyping platform. And in the scope of field-based phenomics, this piece right here is obviously happening in the field. We'll then shift into looking at data processing and how we can take that raw data, process it into a form that's usable and useful for genetic analysis, which in our scope basically means that phenotypes, individual data points are assigned to genetic entries. So whether you're working on a breeding program with 1,000 or 10,000 entries, whether you're working on an agronomic experiment with multiple treatments and replications, you need to take and process this data and assign it to entries in that experiment. And so we'll then focus on data processing. Down the road, we talk about genetic analysis. And so how do we take that information, use it for prediction modeling, and use it for association mapping or whatever approach you're interested in. And so for this workshop, we're primarily going to be focusing on this piece of the equation. We will just briefly touch on, but won't be focusing on genetic analysis. Working under the assumption that once these data have been assigned to genetic entries, that this scope of analysis is a very rich and dynamic field with many different approaches, very available software, and statistical expertise. And so just for your overview, this is where we'll really be focusing this workshop, taking from the field raw data, proximal sensor measurements, being able to process those, assign those to entries in the field experiment, and based on our field design, assign those to treatments or genetic entries. And so the first day today, we'll be talking about high-throughput phenotyping and sensor basics, thinking about the design and implementation of experiments, the design and implementation of platforms, many different types of sensors, and the strengths and weaknesses of each sensor type, and how these can be deployed and used differently depending on your approach, your crop, and your phenotyping platform. The next day, we really talk more about vehicles and integration of these, thinking about different types of platforms. So we'll overview strengths and weaknesses of different platforms. We briefly touched on the ground-based vehicle and the UAV. There's many, many different types of platforms. And so we'll touch on strengths and weaknesses of those and focus then on sensor deployment, how these are actually deployed, into the field, getting data, and the data logging. And so different approaches for data logging and how this provides raw data level that we can then use for processing. On the third day, we're going to focus more heavily on data processing and analysis, how to use the georeferencing approaches. We'll have workshop exercise on this, actually working through real data sets to do the geoprocessing and analysis. We'll talk about additional challenges in data processing and then inverse modeling. And then day 4, we'll really finish up with data management, talking about how to appropriately handle large amounts of data, keep this organized in a way, and then we'll get into also image analysis. And then on the last day, we will have time set aside, particularly in the afternoon, for everyone who's still around to basically have open roundtable, one focusing on follow-up from any of the exercises, anything that you would like, any one-on-one follow-up. Also will be a time to arrange roundtable discussions on specific topics for more in-depth discussion of what's come up through the week. And so some logistics, we already touched on this. Please do. We'd like to continue to publicize and to make available to the community this workshop. And part of that is having the photo release to include in our news and press release from this workshop. Please do keep in mind that we'll be going to the field, we'll be going to the laboratory, and so be safe around the equipment. You've already been oriented to the wireless network, and so this is where I want to orient you to the website, where will be a real key location for you to get all of the workshop materials electronically, and they will be posted throughout the workshop. So I'm going to go there now just to show everybody where we're at. If you go to our Field Phenomics website, and you can type in workshop/2015 HTP workshop, or you can go directly from this workshop link here. Please do go visit this site now. We will be posting all of the logistical information. There'll be download links for all of the workshop material, for all of the presentations, for basically everything you need for the rest of the week. We'll be posting here in electronic form for anything that you will need during the workshop. And so if you go down here, what's available already is the first day's schedule. Download links here on the right for each of the presentations. And then importantly, when we have the workshops, let me refresh this here. Your workshop material will be posted on this website. And so for any of the workshops, you'll be wanting to go to the website and download the workshop material, whether it's the instruction sheets or the data sets, will all be posted here. Okay? So I'd encourage everyone to go and make sure you're able to access that site. If you're having any trouble, please find me, and we'll make sure you are oriented and able to access all the materials on that website. And so since you made it here, you're already a bit oriented with our daily transport. We'll be leaving around 7:30 from the hotel area. We do have a main bus that we'll be taking back and forth, and we have a few other smaller vans that will also be leaving at that time. And we'll be, at the end of the day, when we end up, we'll be leaving collectively back to the hotel area. So please, at the end of the day, if it's 5 o'clock rolls around, bring yourself back here to the front, and so you're not spending the night here at MAC. You can, here's the contact information for myself, for Steve, Jeff, and Pedro, and all of us who are available and driving transport for the week. And so if you do have a transportation emergency, keep these numbers handy to be able to contact one of us. And so we are having a Wednesday evening social at the park in Chandler, and so we're looking forward to this. We do want to highlight that the event has been sponsored by Monsanto and the cotton breeding group at Monsanto. So we're pleased to have the social this year with their support. Transportation will be provided. The daily transport will take everyone back to the hotel that evening, and then we will shuttle with the smaller vans. It's just about a mile away, I believe. We will be shuttling back and forth everyone over to the social site at the park. And so please RSVP today. We are expecting, I think, everyone to join, but please do go ahead and RSVP. We should probably, what's the logistics for doing that, Jeff? Just on the sign-up sheet or something?
I think we'll circulate a sign-up sheet.
Okay, so we'll circulate the sign-up after lunch. Please, if you're not going to join, let us know, but please do RSVP just so we can have an accurate head count for the social on Wednesday. Andy, is there any other announcements for that?
There are any beer drinkers?
Oh, yeah.
Separate sign-up list for that. That's not being contributed, that would be your self-contribution.
Okay. So for drinks, for evening drinks, you can see Andy and sign up and chip in, and then I think everyone will be taken care of on that side as well. So in the event of the emergency, our two local contacts are Bob and Pedro. No, just Pedro. Yeah, this didn't get updated, sorry. Just Pedro. And so keep this number handy. Pedro will be the main point of contact for any local emergencies. Okay? And so we'll conclude there. Are there any questions on kind of the overview on the week, especially on any logistics as we get started for the workshop?
For those of us that may need to leave around noon on Thursday,
Yeah.
should we have arranged for a taxi to fix us up here?
So the question was, for those leaving early on Thursday, did we have transport arranged back to the hotels?
I think between the two U of A vans
Yeah.
and the other vans, we'll make arrangements. I think last time there were a few people who rented cars and were going back, so we'll just figure it out. One way or another, we'll get people back in time to the flight.
Okay.
I think, Thursday morning, we'll start checking.
Yeah, so tomorrow or Wednesday, we'll send a sign-up sheet around. For those leaving early, we'll get the times, and then we'll, as we did last year, we'll take earlier times on Thursday. We'll shuttle vans back and forth in groups of 5 to 10. Great, thank you. What's that? Has everyone been able to get a hold of a photo release form? Is there anyone that's, we got a couple here that didn't get a photo release form? Oh, quite a few. Okay, Jeff has them here. I'll pass them out. Oh, this middle section. Okay, yeah, the middle section here didn't get any photo releases. So for the photo release and for the medical emergency information, please just turn those directly into the registration desk. Great, thank you. Any other questions on logistics for the week?
Okay, good morning, everyone. So, first thing I'd like to discuss with you this morning is the first thing that you do when you decide that you want to do a phenomics experiment in the field. What do? You have to think about how you want to lay that out and plan the experimental design. So Jesse talked a little bit about this already in how you might set up a field for phenomics. I'd like to go into a technology that we use quite readily here at Arizona pretty much before we do any experiment, and that is GIS. Phenomics experiments are highly geospatial in nature. It follows from precision agriculture, where we were beginning to learn about how to treat different zones of a field differently, and beginning to think about agronomic data collected geospatially. In terms of phenomics, our field treatments are going to be imposed geospatially. The sensor data that we collect has to be tied to GPS positioning data to locate it. Sensor data must be then referenced to a treatment plot so that we know what treatment imposed at a particular location in the field should be associated with what sensor data was collected at that location. So the aim of high-throughput phenomics is the collection, processing, and analysis of geospatial information. And as it's been said already, it's really an extension of precision agriculture and all of the technologies that we've been studying in precision ag over the last 2 decades applied to plant breeding. Geographic information systems offer utility for laying out your fields and for data processing. And this tool can, if you choose, there are other ways to, of course, deal with data, but if you choose, GIS can be a technology that kind of circumscribes your field-based phenomics efforts. So I'm going to go over just kind of the very basics of GIS with you over the next 10 minutes or so. Fundamentally, the shapefile is a very key piece of GIS. This is a data format that is used to represent geospatial data. It's a data standard that was developed by a company called Esri. Esri is the maker of ArcGIS. You're probably familiar with that, many of you. But the important thing is that the shapefile is compatible with many other GIS software. It's become such a standard that many other GIS software other than Esri can read and interpret and use shapefiles. Shapefiles describe what's called a vector feature, or a shape of a particular object on the Earth. That could be a point, some information that was collected at a point on the Earth. It could be a line, like a road, like a stream. Anything with a linear aspect to it can be represented as a line shapefile. And a polygon shapefile is something represented as an area. So, for instance, your plot. A plot would be represented as an area, a polygon shapefile. Within the shapefile, each feature, or each one of these shapes, has a set of attributes or data associated with it. And so this is how we tie the spatial aspect of some characteristic of the Earth to the data associated with that characteristic. The purpose of the shapefile is to store geometric location and attribute information collectively together. And so this is a view then of a typical GIS software layout. On the left you have what's known as the map view, where you see some points. This would be a phenomic study that we did where we had the tractor going back and forth collecting many points over this field. And for each one of the data points here, there's a corresponding line of data or information. There's a direct link between the attribute table view of the GIS and the map view, so that you have your spatial characteristics tied with the data or information at that location. As I mentioned, the plot maps can be represented as a polygon shapefile. So you see that represented here on the map. These polygons each represent one plot for a phenomic study that we have done here. The purpose of the plot map in GIS is to make a way for you to associate data that was collected within a plot to the attribute information for that plot, which would be, for instance, the cultivar planted in that plot, or the amount of irrigation applied to that plot, or the nitrogen treatment, or any other treatment that you imposed at that location of the field would be contained in the shapefile for the plot map. An important point is that these plot layouts can be pre-planned in GIS. Before you ever set foot in the field, before a tractor ever goes out into the field, you can use GIS to outline your field plots. And that's how we do it here in Arizona for most of our studies that come out of USDA. We have an experienced GIS technician over there who works on laying out all of our field experiments in GIS before anybody ever sets foot in the field. One of the reasons for that is that, of course, in Arizona we rely on irrigation of many different forms, be it furrow or drip. Particularly in the case of drip, if you have drip lines already installed in the field, you want to make sure that you're going out and planting directly on top of those drip lines. So you can see then that it's very important to pre-plan the geospatial aspect of your plot layout because to ensure that you're planting over your drip lines. So there are many ways to go about doing this. What we typically do is go out into the field with a GPS rover and measure the locations of, say, those drip lines. Then we can take that information back to the laboratory into the GIS. And if we combine that information with known information for, say, your plot width that you want, or the plot length and the arrangement of plots in the field, you can use GIS tools to physically lay out this plot on the screen before you ever set foot in the field. And through this process, we create a plot map as a polygon shapefile. Then we can, based on what we decide for experimental design, you can assign a particular treatment to a particular plot. Sensor data. That's going to be the topic of today, and GPS is the main topic of tomorrow, and how you integrate those two things. Sensor data, which collects some information about the crop, and GPS data, which tells you where that data was collected. Those data can be represented in GIS as a point-based shapefile. This is an example here, zoomed in. This would have been a tractor with 4 sensors across the boom that traveled back and forth across this field. And you can see the data points that were collected by the tractor. So point data, or data from sensors, is usually represented as point data in a shapefile. And finally, Wednesday, we'll arrive here. So the material over the next few days will take us to this point where, and this is again showing the GIS and a tool that I've created, which will be a part of the exercise on Wednesday, where we can actually do the geoprocessing step necessary for relating sensor data points to the treatment plot that those points fall within, so that we can essentially tie the information collected by those sensors with the treatment condition that was imposed at that location in the field. So the main points here of this short presentation is to emphasize the geospatial nature of phenomics and the idea that you can begin thinking about this before you ever set foot in the phenomics field. We have a capability to do that. GIS is a very useful tool for handling this geospatial data, and we use it very readily for all of our phenomics and other field research here at Arizona due to our systems we have here. We lay out fields prior to planting in GIS, and then we come back later after we've collected all of our data, and we use GIS again to geolocate sensor data within treatment plots. So this short talk was just to kind of get you thinking about the next 3 days in which we will be moving in more detail and depth over all of these topics that I've mentioned, arriving on Wednesday with our exercise on georeferencing. And so I'll ask if there's any questions or on that. Totally clear. All right, Jesse, next up.
Good morning. I'm Andy French. And what I'd like to do is introduce those of you who don't know about thermal infrared and remote sensing. I'd like to give you an overview of that and persuade you that if you're going to do any phenotyping, that it's a powerful technique to use, deceptively simple, but amazingly complicated. So just some guidelines on here and how you can implement thermal infrared remote sensing in a proximal sense. So this is the overview here of how we do proximal thermal remote sensing at MAC right behind us in the cotton fields here. Down in the lower left is our phenotyping tractor currently in Texas being repaired, but this is the 4-arm device, high clearance tractor going through cotton. It has thermal infrared sensors on all 4 row positions, pointing straight down and also pointing forward at 30 degrees to minimize soil contributions. This is airborne view of the cotton field back in 2012. This is how that apparent airborne remote sensing looks like, but taken from a tractor. So it has the appearance of airborne sensing, but it's done from the tractor. And this illustrates the change in temperature over the course of a day. So just a little bit of background. Thermal infrared remote sensing detects crop transpiration and water stress. And it seems sort of an obvious technique to use, but it wasn't always so. In the 1980s, thermal infrared techniques were almost killed at NASA on their satellites because it was perceived by some as too inaccurate and unable to accurately measure latent heat and transpiration. But fortunately, some people prevailed and showed how those techniques can be improved and made accurate. So now we're applying it not just from space, but we're applying it from a few meters away. Last summer, we flew Aranca, which is a 1959 modern airplane, wooden aircraft with some modern FLIR thermal infrared cameras. We had some nadir views, ones that aren't so dramatic as these oblique ones that we've taken here, but this illustrates the huge difference in temperature between a droughted crop and a well-watered crop. So the blue colors are cooler colors here, and these are where we're well-watered, every other row here of cotton, and in between are the droughted treatments here. This is a drip irrigation system, and right in here, we're flying overhead when the tractor is going through the field. Those little arrows indicate maximum and minimum temperatures that actually occur on the tractor. So if you look through this field, you can see, for example, in the droughted treatments, that there's some variations within the plots that indicate possibly genetic differences. Plant temperatures vary dynamically, and that's why this talk. It's not just taking something you buy from Home Depot and point the thermal infrared radiometer at the plant and get a temperature and go on to the next one. They change from the morning when they're all about the same, the surface is close to isothermal, to when they differentiate near midday, and then at night, again, they cool off. This shows you here the well-watered treatment here climbs at 7 o'clock in the morning from 25 Celsius up to about 33 Celsius, whereas the droughted treatment climbs as high as 40 Celsius on average. And the air temperature, by the way, is not always the same as the plant temperature. They can differentiate quite a bit. So the focus of this clearly is to map temperatures in an airborne sense, but using ground technology. And you've been introduced to NDVI and mapping so we can match up the NDVI with the surface temperatures to get better transpiration estimates of the plants. Well, thermal infrared is complicated because it has spectral dependency, which we normally don't think about too much. It's much longer wavelengths, 10 micrometers, than the solar radiation that we deal with. The signal is substantially less, and it's affected by the atmospheric properties. In particular, at these wavelengths, at 10 to 14 micrometers, we have what's called an atmospheric window, which means that if you look straight overhead, you see very cold temperatures you see through the atmosphere. But that atmosphere also radiates its energy down towards the Earth, and those effects have to be removed to get the most accurate surface temperature. The atmosphere has an influence on when you measure the temperature over a series of distances. In the window wavelengths, 8 to 12 micrometers, there's a very small dependence on distance to the plants, but if you have an infrared thermometer that's measuring the 7 to 8 micrometers, that effect is very strong. So it means that you have to select your sensors carefully. Field of view. We'll have this in an exercise on Tuesday afternoon, several ways of illustrating the effect of your thermal sensor and how far away you are and the specification of the thermal infrared sensor, and there's the equation there. Up there, it's a tangent function. But generally speaking, when you buy sensors, they're non-focusing. They just collect a cone in the field of view. And when you point it at plants, you might be picking up a little bit of sky temperature, which is very cold, or you might be picking up a little bit of soil temperature, which is very hot, neither of which contribute useful phenotypic information. One of the complications of thermal infrared sensing is also the emissivity. That's the efficiency at which the temperature is radiated by the surface. So plants are typically thought of to be near black bodies, meaning that they're very efficient, close to 1. If they have something less than 1, they're going to reflect a little bit of radiation from the atmosphere and complicate your observations. In the same way that you're measuring soil temperatures or maybe sky temperatures themselves, reflected radiation have no relevance to the target of interest, which are the plants. And that means that you have to consider the spectral response of the sensor you buy. Most of the sensors, the inexpensive sensors, try to open up the spectral window to maximize the signal to noise, and the consequences they bring in observations that aren't signal. This shows the typical sensors that we use, 8 to 12 micrometers here. These blue and green curves illustrate spectral responses for satellites. We don't have that kind of resolution for tractor-based sensing, but it shows you that they are located to optimize the identification of surface emissivity, which is illustrated by bare soil here out of Oklahoma. This is an example of how that emissivity can drop close to 80%. What's the impact of that? That impact is it can change your apparent surface temperature by several degrees. And that several degrees has, again, nothing to do with the plant transpiration you're trying to assess. Here's another example of emissivity response. Typical water emissivities are flat, close to 1 here, but some soils, as I showed you previous slide, have low emissivities at the shorter wavelengths. Dry grass, so when you're looking at senescent vegetation perhaps, the emissivity relationship is inverted where it gets lower at longer wavelengths. These are just to point to you that the temperature that you observe is not necessarily the temperature that you want to end up with in your analysis. Atmospheric correction. For what we do, you have none of the complications of satellite remote sensing because you don't have to look at the long path lengths from space. However, you're not immune to the atmospheric effects because, as illustrated by this arrow here, this is your overlying sky, and it radiates cold temperatures down to the surface, which are reflected into your sensor. So you have to make an additional correction for that. This is a long list, which I won't read through, but to show you some of the checklist of what you should do when you're speccing out sensors for your phenotyping systems. There are thermocouples, thermopiles, microbolometers, thermistors. The array is quite wide. But what the key point here is that most of the sensors that you use on tractor-based systems are these thermopile systems here, which means that you need a reference temperature. So now you're no longer measuring your temperature of your plants, but you need a reference temperature. And how that reference temperature is measured is critical for your accuracy. There are several commercial products that you can look at. We have Representative Mark Blomquist in the back row that will present on Thursday the commercial perspective, and I encourage you to contact him on the practicalities of remote thermal sensing. Here's another one. Everest EnviroTherm is made out of Tucson, Arizona. Another one called Omega. There are many, many others. You can buy out of Home Depot that are good for measuring circuit breakers, but they aren't good for measuring plants. So here is a suggestion for you when you look at sensors. Look at the specifications and see what the spectral window is. If it's wider than 8 to 14, steer clear of it if you can. Check the temperature accuracy. Most of these things are designed for looking at molten steel. It doesn't do you any good if you're doing phenotyping. 0 to 70 is a good range. You need precision to better than 1 Celsius degrees. Check what they claim for their calibration accuracy. Most of the calibration is quoted in percentages. So you need to translate those percentages into temperatures that you observe for plants, which are commonly 30 Celsius to 40 Celsius. Check the response time. If you put these things on a tractor and you're driving down that row at 3, 4, 5 miles an hour, you might not have a fast enough response time to get a good average for your temperatures. So check that response time. Operating environment. Where we are, it gets bloody hot in the summer. So you want to make sure it can handle the 40+ Celsius temperatures. View angle, as I mentioned before, is very, very critical, because if you point that at the wrong angle, you're not measuring what you think you are. You might be picking up some sky temperatures. Data logging. These cheaper sensors can collect a small number of points, but they aren't practical value for phenotyping, where we need hundreds to thousands of measurements. So you need to provide a mechanism for taking that data, which is typically analog, and putting it into a data set and merging it in the GIS, as Kelly mentioned previously. Metadata. Metadata. I think that will be one of the messages of this theme, is the data are no good unless you know where they came from, what sensors they came from, the calibration, the whole history of this. All very, very important to make sure that the results are meaningful. Ancillary data. You need weather data of some kind. Typically, people use state networks for weather data. The state network might be 20 kilometers away. That probably is not very representative of the data within your phenotyping field. I would encourage you to include a local weather station of some kind that's representative of your experiment. Hard to read slide, but this is what I want, and it's in your notes. This is a correction equation that you should apply. It does not apply huge correction to your temperatures, but it improves the accuracy of your temperatures to be more meaningful for plant transpiration. This is it. It's the fourth root of a weighted temperatures of your sensor that you've observed, and the sky temperature, which you can read if you point the sensor straight overhead. And we're going to illustrate that in a workshop exercise this afternoon and tomorrow. And you can improve your accuracy. So all the temperatures should be standardized in this way. Lastly, I think this is my last slide. You want to maximize the signal by considering that if you deploy multiple sensors, they may have different accuracies. And those accuracies you ascribe to phenotypic differences, which in fact are actually instrumental differences. One way to do this is to provide reference checks at the beginning and the end of your survey, just in the way you do with a regular land survey. Do temperature differencing. If you're able to do it logistically, measure temperatures early in the morning when the plant is mostly isothermal, and then the sensor-to-sensor differences can be normalized against the daily change. So you're looking at the daily change as opposed to a single time of day. Because if you make an observation an hour later than you do on a typical thing, you're going to get a different apparent temperature, and you're going to ascribe that to a phenotypic difference that isn't real. It adds an acquisition burden, and we can show you some examples in the field and how this is done. These are just some plots from actual experiments to illustrate that the temperatures, how they vary widely over the course of the day. At sunrise, see here most of the temperatures are isothermal. Air temperature, soil temperature, and vegetation are all almost exactly the same at this point, just after sunrise. And then they diverge. And what's interesting is that air temperature can be higher or greater than or less than plant temperature. It's highly dynamic, so don't assume that your plant temperatures under well-watered conditions are the same as air temperature. And this is a closer look at the temperature variations within an hour. See, this is a scale between 19 and 24 Celsius. Quite a wide range in temperatures. The soil temperature is well behaved, and this has nothing to do with your phenotypic assessment. This is the vegetation. This is a signal that you're interested in. You can see that there's noise here in the order of 1 Celsius. So this is the summary. Thermal sensing provides a very powerful stress response, but you have to be sure you collect the data with minds to the diurnal variation, the calibration of your sensor, the spectral specifications of your sensor. Make sure that you're logging this with plenty of metadata so you can understand where and when, how they were collected. Apply the corrections to the sky. Try to collect it as quickly as possible so you don't have some diurnal effects confounding your results. And as a last point here, you can go a further step and estimate evapotranspiration and crop water stress indices if you have the capability to do that. And that's it. Thanks. Yes.
Okay, so yeah, and you may have covered this already. I apologize if you did. And we had a question that's, what is the difference between air temperature and plant canopy temperature?
The plant canopy temperature is the surface, it's the skin temperature of all the leaf and stem elements. Whereas the air temperature is a temperature measured at some standard reference height. Typically 2 meters would be a standard temperature height. But if you measure that at a different height, you'll get a different air temperature. So you have to agree on what height to measure your data because it's affected by your surface roughness. Yes?
Is the general rule of being isothermal at sunrise true wherever you're at? I mean, there's places in the Midwest where the overnight temperature is still up in the 80s. Is it still isothermal at sunrise? Regardless?
Well, no, you'll have to, there might be dew, for example. Yes? Oh, I'm sorry. So the question is the isothermal assumption correct in all locations? And actually, it may not be. It's what I'm sorry, I have a Southwest bias here. This circumstance happens more than not. But if there's dew, for example, I think that assessment might be something you have to check, particularly the Midwest. Any other questions? I think Jeff White is up next.
Up next, what I wanted to say is that because we have the brake material here, we're going to go out, just walk out to the field. It's basically just down the road, what, about 100, 200 yards. And Pedro will have his tractor up. So this will be your first chance to see a vehicle in the field. Pedro, you want to say anything about it?
A couple of comments before as far as the transition to the field. First, we're going to a break. in the schedule, we're getting into a break. So there's time if you guys want to grab something to eat. There's that table there to your right. There's water and other beverages. So feel free to do it. This is the time to get something, some snack or something else. As you then exit towards the field, you can do that through that door or that door, either one of those two. But regardless, you need to walk towards your left to the paved road and then walk in that direction, which is south. Okay, there's these plots here, we cannot go over them walking. So just use the paved road on that section. And we're gonna be walking in that direction. You'll see us, okay? Anything else, any other announcement?
I guess just to say, if you still got your medical or whatever your medical information form or the photo release form, if you could just take them back. Mike, you want to stick your hand up? Just stick them on the table by Mike, and I'll pick them up. Okay? And I guess just to check in. Yes. Other questions? No, your laptops will be fine in here. Yeah.
Everything is safe here. You can leave your equipment, your computers. It's fine. It's safe over here. All right. So we'll see you guys as soon as you're ready. We'll see you in the field in that direction.
Good.